Now maximum impedance. So previously in case of series resonance, you probably observed that in case of series resonance our impedance characteristic was just like this. That means at the resonance condition the impedance was minimum, but in case of parallel resonance this is the opposite scenario. That means here at the resonance condition the impedance should be maximum, or I can say close to maximum. Basically is it's close to maximum, the maximum impedance occurred at some other frequency which is Fm. So maximum impedance condition Fm. So to derive this maximum impedance equation, first of all we can use, let's say we have the equation of Zt, right? Since Zt is the total impedance of the circuit, that means it consists of the resistance, inductance and capacitance, and this is the peak value. So you know that to find the peak value we generally in mathematics we generally do the first derivative and then we put the derivative equal to 0, from where we generally calculate the maximum values. So we can do this sort of calculation and after this sort of calculation we will find the value of just like this. And don't be worried about this formula, this is more like of this one. If we first of all let me clear this wall. So this is more like this formula, that is Fp equal to 1 over 2 pi root over LC 1 minus RL square C over L. But in case of Fm, if you notice here we have 1 over 4. So this is just a single difference. I think you can memorize this, and this formula actually came from, as I mentioned, we have the equation of Zt, then if we get a first derivative of this Zt and then if we put the values equal to 0, just the maximum value theorem of mathematics. So then we will find this sort of equations. So you don't need to do that calculation in that exam, so don't worry. Generally that maximum frequency point, that means the frequency where the impedance is maximum Fm, this is generally greater than Fp, and also the Fs is generally greater than Fm. So this is generally the case. So Fs is generally greater than Fm and Fm is slightly greater than our Fp. So this is the resonance curve for Zt versus frequency for parallel resonance. So if you notice this Fm, that means where the impedance is maximum, just some value before we have our Fp, that is the parallel resonance. This is the maximum impedance. So now for that maximum condition, obviously the circuit's total impedance will be R, and along with R we have parallel XLP and XC, that means the total circuit impedance. You can understand that this is a simple calculation. We have R, then along with R we have our XLP, and also we have our XC. So obviously the total impedance will be the combination of these three in parallel. Now since they are in parallel circuit, so obviously the voltage across all of them will be equal. So Vc equal to Vp. That means let's say this is the parallel branch and also we have the inductance and resistance. So if we consider this as a Vp and also this is Vc, so both are equal. So both are equal, and obviously you know that from Ohm's law V equal to I multiplied by impedance for AC circuits. So that's why Vc equal to MP equal to I into Zt. So Zt, that means the total impedance of the circuit. Now the quality factor. So you already know that quality factor equal to our reactive power divided by our resistive power, that means the real power. So our reactive power obviously Vp square divided by XLP. Now you may ask why we considering voltage rather than current, because in case of series resonance we generally write it I square, and now in parallel cases we are writing it V square over impedance. Why? Because in case of parallel, we know that the voltage is constant for all this component. That's why here we are writing the power equation in terms of voltage. But if it is a series circuit, then we generally write it in terms of current, because in case of series circuit, the current is constant across all the series components. And since we are performing calculation for parallel circuits, that's why we have written this equation in terms of voltage. So the reactive is Vp square over XLP, and similarly the resistive one is the Vp square over R. So now obviously this R is complex, that means R is a parallel combination of RS and RP, and Vp is the voltage across the parallel branches that I already mentioned, this voltage. And from here you can write that it will be just R over XLP, and R is just the RS parallel RP that I mentioned. And also we can write this XLP equal to XC, that is the serial parallel resonance condition, right? Previously we have derived here. So this one, so that is the condition parallel resonance. So obviously we can put XC instead of XLP. So this is the equality factor equation. We may need it in circuit solutions. Now for an ideal current source. So what is an ideal current source? For ideal current source, the source resistance is generally infinity. So when the source resistance is infinity, in previous circuit obviously we have R equal to RS parallel RP. So whenever that let me draw it first. So let it the RP and let it RS. So whenever this is infinity, that means this is an open circuit, so obviously the only resistance present is the RP, so we can write it RP. And this is also true, approximately true, for very high value of RS as compared to RP. So whenever we have a very high value of source resistance as compared to our RP, then we can convert that R as to just RP. So then we can write the quality factor equation just RP over XLP, and then the value of RP and XLP, if we put them in previous we already calculated this value, then it reduces to just XL over RL. So this is actually the QL. So obviously remember, for ideal source, or when that RS is very higher than RP, then this QP equal to QL. So what is QP? QP is the Q factor, that is quality factor for our whole circuit at parallel resonance condition, and QL is just the our component was okay, let me clear it all. So our inductive components have a inductance and a resistance with it, right? So this was RL and this was XL, and for this portion only we have the Q factor, that means Q factor of the coil was XL over R. So this one, XL over RL. So whenever that condition satisfied, then QP equal to QL. Now the bandwidth, so bandwidth equal to F2 minus F1, just like similar series resonance condition, and the answer appears FR over QP, just like the series resonance condition. In case of series resonance, we have Fs over Qs. So remember this equation also. Now in case of series resonance, I also derive the equation of the corner frequencies, that means F1 and F2. In a similar manner, this can be also derived. So here this Z equation is given. In a similar manner, some equations have found, and then we can have this sort of equations, two equations for two corner frequencies F1 and F2. And to be honest, you need to remember this formula, since you need to solve some maths where corner frequencies are asked. So for example, a circuit is given and a question is determine the corner frequencies, then obviously you need this formula. So it may be hard to remember, but you should remember this. And if you notice closely, there are similarities between these formulas, because this first formula is just a minus, and here in the second formula there is just a plus. So all things are quite similar here. So these are the two expressions for the corner frequencies. Now effects of QL greater than or equal to 10. So in case of series resonance, I also showed you that when the quality factor is greater than 10, then some approximations could be done. For example, in case of series resonance, we showed that the resonance curve was quite symmetric, right? That means when the Fs was the middle point of F1 and F2. So this sort of approximation also possible in case of parallel resonance. So I will show you now. So all the equations that I just showed you in previous session, so this could be reduced to simpler expressions. So whenever we consider a QL very greater than or equal to 10. So first of all, the expression of inductive reactance, that means XLP. So this one is already derived. You can find it in the upper portions of this PDF. And then if you divide this equation here, so it will be RL squared over XL plus XL square over XL. So here you can have just XL and here RL square over XL. Then if you multiply XL to both numerator and denominator, so it will be just like this. And then you can integrate the quality factor here, because the quality factor of that inductive coil, that means only QL, was just the XL divided by RL, right? So if you notice here, this is basically XL square and we have RL square here. So obviously we can write it in the denominator, we can write it XL square over RL square. So then we can write it as QL square. So now the expression appears as XL over QL square, and XL was already there. Let me clear it all. Okay, so now if the QL greater than or equal to 10, so when this QL greater than equal to 10, we can say that 1 over QL square will be very less than 1. Why? Let's say this QL equal to 10, right? So when this 1 over QL, so it will be square, so it will be 1 over 10 square, that means 1 over 100, so it will be 0.001, right? So it will be obviously very less than 1, and whenever this value will be, let's say 100, so when it is 100, it will be more 20 here, so it will be more 0 here before after this point. So obviously this will be very less than 1, and when this is very less than 1, this portion we can write just 1. So then this appears as just XL. So whenever this condition satisfied, that means the QL greater than equal to 10, we can write XLP equal to just XL. And also we know that our condition was XLP equal to XC, right? So obviously we can write XL equal to XC as well. Now the resonant frequency FV. So previously our resonant frequency expression was FV equal to Fs square root over 1 minus RL square C divided by L. So this was our expression. Now we will operate on this portion first. So RL square C by L, we can write 1 over L over RL square C. Then we can multiply omega to both numerator and denominator of the denominator. Then here we have omega L, and here we have RL square omega C, and then we know that XL equal to omega L. That's why we can write XL in this region. Then also 1 over omega C equal to XC. Then we have also another XC. So now the expression appears like this. Then we know that XL equal to XC at this condition, resonance condition. Then obviously we can put both as XL, so it will be appear as 1 over XL square over RL, and obviously XL over RL equal to the quality factor QL, so it appears as 1 over QL square. So now the expression would be F equal to Fs root over 1 minus 1 over quality factor square. Now again, if that quality factor is greater than equal to 10, obviously 1 minus 1 over quality factor square equal to close to 1. just the similar calculation, because this portion will be very less than 1. So 1 minus very less than 1, let's say very 0, and then 1, so we can write it equal to 1. Then the expression is similar to our series resonance condition. So whenever we consider that QL greater than equal to 10, then Fp appears equal to Fs, since this term appears as just 1. So we know that the expression of Fs 1 over 2 pi root over Lc. So when this condition is satisfied, we can write that these two are similar.